Now, we all know that all planets are round. There are no square ones so far, and that's because of gravity. Well, roundish at least, as not all of the planets have perfect proportions. But did you ever wonder about the shape of the universe itself? Is it also round because of the same forces? Well, not really. Based on what information we have so far, the universe is actually flat? According to the principles of general relativity, space has the ability to curve. This opens the door for the universe to have three potential shapes: a flat plane like a sheet of paper, a closed sphere like a bowl, or an open saddle-like curve. This isn't just a matter of academic interest, you know. The universe's shape has direct consequences on its ultimate destiny. One cosmologist from Princeton University explained it beautifully. The shape of the universe is a kind of map to its past and a predictor of its future. The questions of whether the universe will keep expanding forever or collapse at some point, and if it's finite or infinite, all circle back to the question of its shape. Now, to wrap your head around this cosmic question, you need to understand two key elements: the density of the universe and its rate of expansion. Let's dig into this a little. Around 68% of the universe is made up of dark energy, while 27% is dark matter. The rest, which is normal matter, if you'd like, makes up the stars, planets, and other cosmic bodies we're familiar with. When we talk about the density of the universe, we're referring to the quantity of normal matter packed into a given volume of space. Now, if the universe is denser, it also has more gravity. In this case, the gravitational pull can overcome the force of expansion, so the universe curls up into a sphere. This shape is known as the closed model, where the universe ends up looking like a gigantic cosmic ball. Imagine a world that's finite but without boundaries, a contradiction for sure. In this model, an adventurous explorer could travel forever through space, never bumping into a wall or falling over an edge. Alternatively, if the density of the universe is low and not enough to halt the expansion, then space distorts in the opposite direction. This results in an open universe with negative curvature that resembles a saddle, like on a horse. Despite these two potential scenarios, most scientists agree that the density of the universe is just right, which means it expands proportionally without curving. But what does it mean if the universe is flat? It doesn't mean we're living in an infinite sheet of paper. To understand it, consider these analogies. Imagine you're in a square room, walk 10 steps to the next corner, make a 90-degree turn, walk another 10 steps, and repeat this process twice more. You end up back at your starting point, completing a square. Add another dimension to this geometry, since we're not 2D creatures, and whoopee, you have a flat universe. This analogy wouldn't hold up in a curved space. If you have a terrestrial globe at home, you might find it easier to understand this next experiment. Start by placing your finger at the Earth's equator, then trace a line to the North Pole, make a 90-degree turn, and return to the equator. Make one more 90-degree turn and walk back to your starting point. This journey only needed 3 turns, unlike the 4 turns in the flat universe scenario. Still struggling to understand? Here's another way to picture it. In a flat universe, 2 rockets traveling side by side will always remain parallel. This is in contrast to a closed universe, where the rockets will travel along the curve of space and eventually meet where they started. In an open universe with negative curvature, the rockets will gradually drift apart and never cross paths again. So, is there a cosmological crisis at hand? It seems the answer to the shape of our universe is encoded in the cosmic microwave background, also named CMB, which is like the universe's fossil record. Over the past few decades, scientists have measured temperature fluctuations in the CMB to find almost no curvature, indicating a flat universe. Now, the concept of a flat universe is crucial to the standard cosmological model. However, in late 2019, scientists from a university in Rome published a paper arguing that current CMB measurements actually indicate we're really living in a closed universe. How did they figure this out? Well, they looked at how light behaves in the universe. Specifically, they analyzed how light bends because of the gravitational force of matter in its path. Either way, apart from this finding, there's nothing else that would suggest we're living in a closed universe. Most scientists believe this recent discovery is nothing more than a statistical anomaly. But if the closed universe theory turns out to be right, it would shift decades of astronomical findings. If the universe is indeed curved, it must be so large that the observable 93 billion light-years aren't enough to reveal its curvature. It could be similar to standing in a fog, only able to see a small, flat patch of land. Yet somewhere out of sight, the horizon reveals that we live on a sphere. As we continue to probe the cosmos, we might find that the apparent flatness of our universe is just a small part of a much larger, curved cosmos. Its shape is just one of the many things we've yet to figure out about the universe. We can't quite put our finger on why the universe is even here, for instance. We do have some theories, but scientists are yet to be sure. It could be that the universe is like a pop-up, materializing out of an unstable nowhere land. Imagine the emptiest emptiness you can think of, suddenly churning out matter and energy in equal and opposite amounts that tally up to zero. For most of us, it's hard to picture that process. If we follow this theory, who's to say there's only one universe? We might be just one of an enormous collection, a so-called multiverse. For now, we'll just have to wait for the next wave of cosmic measurements to refine our theories, and for scientists to come up with hypotheses that aren't just mathematically pretty, but actually testable. Also, how could we possibly know all the secrets of the universe if we don't completely understand our own biology yet? I mean, if we did, we could, theoretically, solve all of our health problems, right? We might even be able to play around with our DNA, like this molecular Lego, and give ourselves naturally purple hair or red fingernails. Well, time for a reality check, as we're still struggling with this one too. Here's a great example: our microbiome. Our bodies, home to 10 trillion human cells, are also an active city for 100 trillion microbial cells. That's a couple of pounds of bacteria and other microbes, which we absolutely can't do without. They've set up shop in our bellies, lungs, noses, and every other hidden nook and cranny. We're like luxurious cruise ships for these tiny microbial tourists, and we still don't fully understand the implications of this symbiotic relationship. There are still a lot of things we don't know about planet Earth either. We've only ever dipped our toes into Earth's crust, never venturing more than a few miles deep. Everything else is our best guess, from remote sensing and smart physics. Believe it or not, it took us an embarrassingly long time to accept that the Earth's crust is constantly shifting, like Jenga pieces. We only warmed up to plate tectonics in the mid-20th century. We're also still trying to figure out precisely how the planet's inner engine works, and how the swirling conducting materials in the outer core create our protective magnetic field. Plus, with 4.5 billion years of geological chaos, we're sometimes better off studying meteorites or the surfaces of other celestial bodies for clues about our planet's history. Even our faithful companion, the Moon, is a bit of a mystery. Was it born from a colossal collision or some other event? We're still not sure. But hey, the fact that we still have a lot to learn is what makes life interesting, isn't it? That, and the thrill of actually finding an empty parking spot in San Francisco, or maybe even your city.
How was our universe born? And if this seems hard to answer, then how about this? What was before our universe? While scientists are looking for the answer to the most difficult question in history, let's find out what they've come up with so far. In the 20th century, we've shed the light on this mystery, all thanks to this man. Edwin Hubble. One day on Mount Wilson in Southern California, he aimed his telescope at the sky and found out that these random clouds of gas flying everywhere are actually other galaxies, and there are a lot of them. And also, he learned something else, something that changed the world forever. They're moving. So what, you may ask? Well, it meant one very important thing. The universe is expanding. And if it's expanding, then it probably had a beginning somewhere, right? Now, all we have to do is run time backwards and see where the beginning was. It took the scientists many more years to come up with a full-fledged theory, the Big Bang Theory. And here it is. Nothing has ever been anywhere because neither when nor where existed. Do you get it? But actually, no. There was one thing. It was the so-called cosmic singularity, a state of our universe in which it was incredibly small, dense, and very hot. Imagine if our universe was compressed into a small ball. The pressure and temperature inside would be enormous. At some point, it became impossible to withstand them. And here comes the Big Bang. It was an outburst of energy and matter that created everything we see now. Time and space, basic physical forces. It also scattered quarks everywhere. These quarks, tiny particles that make up our world, were all boiling in an incredibly hot cosmic broth. When it cooled down, gravity began to attract them to each other. They gathered into atoms, then molecules, and then into the first objects into the world, stars. And all this happened just some 12 to 14 billion years ago. Alright, now we know how our universe was created, but what was before that? Alan Harvey Guth, an American theoretical physicist and cosmologist, has devoted his whole life to solving this mystery. After learning about the Big Bang Theory, Guth found some flaws in it. For example, the distribution of matter was very even, although it shouldn't have been. Let's hang a balloon filled with paint to the ceiling and lay a white canvas on the floor. If we drop the balloon down, it will burst and we'll see absolute chaos on the canvas. A bunch of spots scattered everywhere randomly. Neither is like the other. But that's not really what the universe looked like. Instead of throwing a colored ball from the ceiling, let's draw a small red dot on the canvas. Now, let's expand it a little more, and capture this all on frame-by-frame shooting. We'll see a circle gradually growing in all directions. That's the reality. The early universe was very even and proportional. That was Guth's discovery, the theory of inflation. Here's what it says. Even before the Big Bang, there was some kind of force that could give the bang a strong acceleration, something that was able to distribute everything in space instantly and evenly. Guth's theory was a success, and now most scientists rely on it. Have you ever heard about the Big Bang? I bet you have. So the history of the universe and its evolution is widely known as the Big Bang model. It claims that our universe began as an insanely hot and dense speck about 13.7 billion years ago. But how did it go all the way from a tiny point to the ginormous world we see and don't see today? We're about to figure that out. Despite its name, the Big Bang wasn't a powerful space explosion. It was the appearance of space everywhere in the universe at once. And the universe itself was born as a very dense single spot in space. No one knows for sure what was before this moment, but scientists are working on figuring it out. Their main assistant is the cosmic microwave background, which still contains the afterglow of the radiation and light left after the Big Bang. Eventually, it may help scientists piece together some clues about the early universe. Just like any kid, when the universe was very young, about 1/100th of a billionth of a trillionth of a trillionth of a second, it experienced an unbelievable growth spurt. Known as inflation, this burst allowed the universe to double in size at least 90 times. As the universe was expanding, it was also getting cooler and less dense. After the insane growth burst, it kept growing, but at a much slower rate. Very soon, the universe cooled down enough for matter to start forming. Everything happened so fast at that time. Light chemical elements appeared within the first 3 minutes after the formation of the universe. Protons and neutrons began to collide, producing deuterium, an isotope of hydrogen. A lot of this deuterium combined and created helium. Then, the process is slowed down significantly, but still for the first 380,000 years after the Big Bang, the intense heat from the creation of the universe made it too hot even for light to shine. The conditions in this early universe were hellish. Atoms collided with such force that they broke into an opaque plasma of electrons, protons, and neutrons. This dense veil scattered light like fog. But 380,000 years after the Big Bang, the matter eventually cooled down enough for electrons to connect with nuclei and form neutral atoms. This absorption of free electrons finally made the universe transparent. By the way, the light unleashed at that time can still be detected today in the form of radiation. A period of darkness followed this era called the Era of Recombination. And then, stars and other bright objects started to form. It happened about 400 million years after the Big Bang. This next period got the name reionization. Some time ago, scientists thought that it had lasted more than 500 million years, but new evidence hints that it might have occurred more rapidly than we thought. During this period, clumps of gas collided and created the first galaxies and stars. These events emitted ultraviolet light, which got rid of most of the surrounding neutral hydrogen gas. That's why we call those times the period of reionization. This process led to the universe becoming transparent to ultraviolet light for the first time. At the moment, astronomers are combing the universe in search of the farthest and oldest galaxies. Such a discovery can help us understand the properties of the early universe. It's like working backwards to piece together the events that happened before. That's what researchers are doing now by studying the cosmic microwave background. Our solar system was born around 9 billion years after the Big Bang, which makes it around 4.6 billion years old. As far as we know, our Sun, orbiting approximately 25,000 light-years from the galactic center, is one of more than 100 billion stars in our home Milky Way galaxy. The most popular idea is that the Sun, as well as the rest of our solar system, was once formed from a huge rotating cloud of space dust and gas known as a nebula. At one point, gravity caused this nebula to collapse. It started spinning faster and, eventually, flattened into a disk. Most of the material that made up the nebula got pulled towards the center of this formation, and that's how the Sun was born. At one point, scientists started thinking that there might be more mass in the universe than what we see. After some research, the concept of dark matter appeared. One theory stated that this mysterious stuff could be formed by some exotic particles. They don't interact with regular matter or light. That's why it's so difficult to detect them. Already in the 1920s, astronomers made an astounding discovery. Apparently, the universe isn't static. It's constantly expanding. Interestingly, when decades later, in 1998, the Hubble Space Telescope studied distant supernova, it became obvious that in the past, the universe was expanding more slowly than today. Why was this discovery so confusing? Because it was long believed that the gravity of matter making up the universe would slow down the expansion process, or even cause the universe to contract. That's why these days the concept has changed a bit. Everything on Earth and everything people have managed to see in space with the help of telescopes and other instruments is normal matter. It's made up of atoms and molecules and adds up to less than 5% of the universe. Around 27% of the universe is dark matter, and almost 3/4 of the universe is dark energy. Astronomers wouldn't even know the thing existed if, several decades ago, they hadn't found out that the expansion of the universe wasn't slowing down. Quite the opposite, it was accelerating. It meant that there had to be some enigmatic force counteracting gravity. It got dubbed dark energy. The European Space Agency's Planck satellite, helped astronomers calculate how much dark energy the universe has to contain to explain the way its expansion is constantly speeding up. Scientists have also built models of how many giant stars formed and collapsed into black holes since the beginning of the universe. The conclusion is very exciting. The vacuum energy in these black holes is almost the same as the amount of dark energy that should exist in the universe. And still, even though nowadays we know much more about the universe than we used to, there are still important questions that remain unanswered. And, of course, dark matter and dark energy remain the biggest mysteries. Another one is whether something existed before the universe was born, or maybe the theory of the false vacuum is correct. It says that our universe exists in a false phase state, which means it's just a temporary thing. What's more, it's only part of a larger universe. If you compare this larger universe with a kettle full of boiling water, the universe we live in will be just a tiny bubble on the surface of the water. But this can't keep going endlessly. One day, perhaps in billions of years, this false vacuum will burst. And then the visible universe around us will instantly vanish with a pop. There won't be any preliminary warning and we'll have to somehow deal with it. In any case, astronomers are working hard to find the answers to these burning questions. The James Webb Telescope, launched in 2021, is believed to be the very tool that can help us to peer back to the beginning of time and explore the evolution of the universe with the help of its infrared instruments. By observing the universe at infrared wavelength, James Webb lets us see things no other telescope has ever shown before. The primary goal of this incredible piece of equipment is to study the formation of galaxies and stars that formed in the early universe. To look that far back in time, we need to look deeper into space. All because it takes light time to travel from there to us. So the farther we look, the further we glimpse back in time. To find the first galaxies, James Webb is going to make an ultra-deep near-infrared survey of the universe.
In 1991, a cosmologist from Stanford University named Andre Linde had submitted an article with the main idea that there was a possibility the universe had been created in a laboratory. His theory said there was a chance an advanced civilization somewhere out there had created our universe. This civilization has made an entirely new cosmos that later evolved its own planets, stars, and intelligent forms of life. 30 years later, many scientists take this theory pretty seriously. They even started talking about things that we, as a civilization, can do to get to such an advanced level. The theory says this advanced civilization decided to add technology that helped to create a new universe out of nothing. It happened through quantum tunneling. It's when an atom can appear on the opposite side of some barrier, even though it's supposed to be impossible, considering the laws of physics of our world. Like if you wanted to pass a tall wall, but you can't pass it with ladders or go around somewhere. Imagine you can just walk through it like a ghost. In our world, it's not possible, but a more advanced civilization perhaps can do it. Plus, they realized how they could create new universes. Right now, on the cosmic scale, we could be a Class C civilization. We don't know how to recreate some things. For example, conditions on the Earth for when our central star, the Sun, goes out. If we manage to become a Class B civilization, we'll learn to adjust conditions to be independent of the Sun. That means we might be able to learn how to live even without it. And if we level up and become Class A, we'll know how to recreate cosmic conditions and produce our own cosmos in our laboratories. We think of the world we live in through 3 dimensions of space: east-west, north-south, and up-down. There's also 1 dimension of time, which means we can distinguish past from future. A 5th dimension would represent 1 more extra dimension of space. The theory of its existence was first mentioned in the 1920s. It was inspired by the theory of gravity by Albert Einstein, who said space-time is warped by matter and energy. We can't perceive these 4 dimensions, but we see how an object moves and attribute it to gravity. And maybe there's some other force, like the electromagnetic force, that's more than 1,000 times stronger than gravity, that could explain things going on in that extra dimension of space. The 5th dimension is curved in a way we can't see it. but the idea about it was mentioned in a string theory. It considers the universe as really small strings of mass energy, not as particles. They vibrate in 10-dimensional space-time, considering 6 dimensions are rolled up way smaller than a single atom. That led to the picture of the universe as a 3D island that floats in 10-dimensional space-time. Also, the 5th dimension might be an excellent explanation to tell us more about dark matter. That's the invisible stuff with a mass, but we can't see it, nor can it interact with ordinary matter. And dark matter is 85% of all the matter in our universe. A recent study suggests the universe is similar to your brain, only at a much, much larger scale. The brain's neural network contains about 86 billion neurons. The observable universe has at least 100 billion galaxies. Both galaxies and neurons have a similar structure. It's a complex web of nodes linking up long thread-like fibers. But in each of these systems, the fibers make up a mere 30% of the total mass, and the remaining 70% are either water in the brain or dark energy in the universe. The ways that galaxies and webs of neurons connect with one another are surprisingly similar. In both cases, the process follows the same physical principles. At the same time, some researchers claim the resemblance between the brain and the universe is only superficial. Your mind perceives tiny details and joins them, and then it comes up with a conclusion that has nothing in common with reality, like the brain is a mini-universe. In billions of years, the universe is likely to expand so much that we won't be able to see any stars in the sky. To turn Earth into a black hole, you'd have to squeeze it until it was the size of a marble. And if you wanted the sun to become a black hole, you'd have to compress it until it's no more than 4 miles across. A starburst galaxy is a galaxy that's forming tons of new stars at breakneck speed. It usually happens after 2 galaxies merge into one. While Earth has only one natural satellite, Jupiter is surrounded by at least 79 moons. In the universe, there are not only dwarf planets, but also dwarf galaxies. They have from 1,000 to a few billion stars. For comparison, the Milky Way galaxy is made up of 250 to 400 billion stars. A supermassive black hole 250 million light-years away from Earth hums the deepest sound ever detected from any object in the universe. It's 1 quadrillion, which is 1 with 15 zeros, times deeper than what the human ear can hear. Planet Kelt 9b is 670 light-years away from Earth. It's an ultra-hot Jupiter. Those are giant, scorching hot planets with a mass similar to that of Jupiter. On Kelt 9b, the heat is so great on the day side of the planet, it tears molecules apart. Any liquid floating in outer space forms itself into a sphere. It also happens in low Earth orbit. Our home Milky Way galaxy is more than 105,000 light-years across. All the planets of the solar system would fit between Earth and the Moon with some space to spare. Black holes spaghettify things. It happens when something gets past the point of no return. Then the black hole's gravitational pull starts to stretch this object in one direction and squeeze in another. The first celestial body that astronomers identified as a spiral was the Whirlpool Galaxy. Its long arms are made of gas and stars, and everything is sprinkled with fine space dust. When you're on Earth, you can only see 5% of the universe. A star coming too close to a black hole can be torn apart by its gravitational force. WASP 12b is a giant planet 1,400 light-years away from Earth. It's made up mostly of gas. Unfortunately, the planet is doomed. It orbits too close to its parent star. In about 10 million years, WASP 12b will be swallowed by its greedy sun. Our Milky Way galaxy and the Andromeda Galaxy, its closest neighbor, are going to meet in a bit less than 4 billion years. When they collide, they'll form one huge elliptical galaxy. One of Saturn's smaller moons, Enceladus, reflects almost 90% of the sun's light. It makes the moon one of the brightest objects in the solar system. But since it reflects sunlight instead of absorbing it, the temperatures on Enceladus's icy surface drop to negative 330 degrees Fahrenheit. The highest mountain in the solar system is Olympus Mons on Mars. It's 3 times as high as Mount Everest. If you were standing on top of Olympus Mons, its slopes would be hidden by the planet's curvature. In our solar system, Mercury and Venus are the only 2 planets without moons. Scientists who are planning to send droids to Mars want to load the machines with lots of heavy equipment. The droids will also be built from stronger materials, all because of the relatively low gravity on the red planet. Everything on Mars is almost 3 times lighter than on Earth. Pluto's largest moon is half the size of the dwarf planet itself. This makes Charon, that's the moon's name, the largest known satellite relative to its parent size.
Empty space is not really empty. At least, that's what quantum field theory says. It's actually filled with tiny vibrations that can turn into virtual particles if they have enough energy. These virtual particles can produce packets of light with low energy called photons. Now, there's something every black hole has: an event horizon. It's a point of no return. That means once something crosses that point, it can never get away. Not even light. And there's an insanely strong gravitational force around the event horizon. Black holes survive by gobbling up gas and stars around them. In most cases, a black hole has a swirling disk of material that surrounds it, called an accretion disk. It glows brightly as all those things that come too close to an event horizon get heated up and torn apart before the black hole swallows them all. As material comes closer, it starts to travel and move faster and faster, going all around the black hole. This makes the accretion disk glow and, at the same time, outlines the shadow of the black hole, which is basically the very event horizon we're talking about. Black holes might even want to hide, but they do so awfully badly. According to Einstein's theory of general relativity, gravity bends and warps space and time. It means that the closer you come to this extremely powerful gravitational pull around the black hole, the more twisted space and time around it become. That's what Stephen Hawking was talking about nearly 50 years ago, and it doesn't stop there. He also suggested that if these particles find a way to escape a black hole, they steal some of its energy. And because of these thieves, the black hole loses its energy as time goes by until it, at one point, completely disappears. He suggested that black holes release energy in the form of thermal energy or heat, which is called Hawking radiation. And this radiation doesn't carry any information. It means that when a black hole evaporates, it destroys all information it had about the star that created the black hole. That way, we can't know what really happened. And it's kind of confusing because the laws of quantum mechanics say the information can't be destroyed. This conflict is something we call the Hawking information paradox. According to Hawking, all this information isn't really lost, but is stored in a cloud of all those zero-energy particles that surround the black hole. He called that soft hair. Now, there's this new study as a possible solution to this paradox. Maybe Hawking radiation is non-thermal. Instead of just releasing plain heat, it's possible the black hole sends out a message in the form of radiation. This message contains important information about the black hole's past, the stars that formed it, and other details we thought were lost forever. It's like a secret code that tells us all about the history of the black hole.
The universe is 3-dimensional. Okay. No, the universe is 4-dimensional. 3 dimensions for space and 1 for time. Okay, duh. What are you talking about? The universe has 9 dimensions. Okay. Come on, guys. The universe is flat. Wait, what? However strange it may sound, all these statements are kinda true. How come? The theory of general relativity allows for the universe to take one of three forms. It can be flat, like a sheet of paper. It can be completely closed, like a sphere. Or it can be shaped like a horse's saddle. It's very important to figure out the shape of the universe. This way, we can learn about its past and future. It can answer crucial questions. Is the universe going to expand forever, or will it eventually collapse? Is it finite or infinite? Here, we need to consider two factors: the density of the universe and the rate of its expansion. Now, hear me out. About 68% of the universe is dark energy, 27% is dark matter, and the remainder is normal matter. That's what stars, planets, and our bodies are made of. And when we speak about the universe's density, we mean the amount of matter packed into a given volume of space. And the density of the universe is so great that its gravity is more powerful than the force of its expansion. Then the universe will curl into a sphere. This is what we call the closed model. The coolest thing about such a universe? Even though it is finite, it has no bounds. However paradoxical it may sound, if you found yourself in this universe, you would travel its space forever without falling over an edge or hitting a wall. But if the density of the universe was low, it would be unable to stop its expansion. In this case, space will warp in the opposite direction, creating an open universe shaped like a saddle. But the most popular theory, and the most bizarre-sounding one, is that the universe is flat. It might be possible if its density is just right, and it expands in every direction without curving negatively or positively. Scientists claim that it's the most plausible scenario, by the way. So, if you're disappointed by our planet's roundness, the flat universe might come as some consolation. But what does a flat universe mean? I mean, our 3D world seems very real. Can it be just an illusion? Nah. The flatness of the universe isn't that two-dimensional flatness you might be imagining right now. To help you understand this concept better, I'll tell you this. In a flat universe, two rockets flying next to each other will always remain parallel. In a closed universe, their paths will diverge, and they will follow the curvature of space and eventually make a loop and meet where they started. And in an open universe, these rockets will separate and never come across each other again. Of course, it'll take a lot of time to prove that the universe is indeed flat. But so far, astronomers don't have even the slightest reason to doubt this theory. All the data they have is consistent with this flatness. For example, the imprints left on galaxies from sound waves that occurred right after the Big Bang also support this theory. In other words, right now, scientists agree that the universe we live in is like a three-dimensional sheet of paper. Good luck trying to imagine this. But if this idea is wrong and the universe is actually curved, it must be ginormous, because those 93 billion light-years we can observe aren't a large enough portion to let us see even a tiny curvature. So, it might be wrong to say the universe is flat. It's probably better to announce that the little bit of the universe we see is flat.
The Milky Way is one of the biggest mysteries out there, literally. It's hard to figure out how big our home galaxy is, and one of the main reasons is because we live in it. Think of it as walking around a mall. You can tell it's big, but you can't be certain until you actually see it from a bird's eye view. The Milky Way consists of billions of distant stars that look like a string of lights from afar. So you just need to measure the distance between these stars and voila, you have the answer. Not really. I might have forgotten to mention opaque clouds of dust blocking your view. Some scientists were stubborn enough to run computer models of how galaxies form and evolve. There's a halo around our galaxy, so the scientists wanted to see if there was some sort of a dead end in the Milky Way. They found out that the Milky Way spreads for 100,000 light-years away from its center. It likely means that the entire galaxy is around 200,000 light-years across. The problem with this estimation is that halos don't tend to have some final border since they simply fade away. It's like pointing a flashlight and trying to see precisely where the light ends. In 2013, the Hubble Space Telescope captured an image of something 25 million light-years away. It turned out to be a spiral galaxy, later called ESO 3738, with at least 7 other galactic neighbors. And this galaxy is as thin as a pancake, a very shiny pancake. The telescope also took a photo of another galaxy cluster 65 million light-years away. It was called IC 335. It's another glorious glittering pancake floating in the vastness of space. The images the telescope took aren't the most accurate. It's hard to tell what exactly you're looking at. These disk galaxies have lots of dust clouds that can stretch for hundreds of light-years across. They're mainly located near the centers of galaxies and are invisible in regular light, but they can be detected with the help of a blue filter. Anyway, this IC 335 galaxy is an oval disk with huge clouds of gas and dust. This means stars constantly appear there. But not all galaxies create stars. A galaxy is born as a giant ball of slowly rotating gas that is steadily collapsing in on itself. As it starts spinning faster and faster, the pancake shape is formed. Ooh, pass me the syrup. It's like spinning pizza dough in the air after rolling it into a ball. The topping is stars, and the sauce is clouds of dust and gas. Are you getting hungry like me? Some galaxies can lose their gas and dust if they become part of a galaxy cluster. Then all these mini-galaxies orbit their common center of mass, with gas separating them. When a disk galaxy dashes through them like a speeding train, the pressure can blow away this dust and gas. From far away, it looks like you're staring at a DVD you're about to play. But if you traveled millions of light-years to get a closer look, you'd see a dim disk filled with stars. You wouldn't even be able to tell you're inside it. You'd also see a bright blob of dust left by the red giants in the middle of the galaxy. Red giants are massive and very bright stars with low surface temperatures. But the images of these galaxies don't actually show us their real color. Cameras make up some of these hues so that you don't have to look at something fuzzy or grainy. People don't actually know the real colors of distant galaxies. Our galaxy has a lot of gas inside, like me, so we don't need to expect our home to dry up anytime soon. In fact, the Milky Way still produces new stars, around 7 a year. But some galaxies fade out when they can no longer create stars. In the industry, they call it strangulation, and it happens when galaxies run out of gas, which means there's no more new material that can be used for star making. Gas and dust aren't the only things you can find in a galaxy. Just like a magician pulling a rabbit, flowers, or other things out of their magic hat, galaxies have other surprises, like planets, those balls of matter spinning around themselves and around other things. Well, technically, planets are far from being perfectly round in shape, but they aren't also flat like spiral galaxies. It's mostly because of gravity. Its force is so strong that a planet pulls everything towards its center, taking the shape of a sphere. In the process, all the edges and anything else that might stick out gets smoothed out. But the smaller a spacebody is, the less round it is. Take a comet. It doesn't always have a smooth surface. It's small, and therefore, its edges are rugged and pointy. Given the size of Earth, it's safe to say the gravity is strong here compared to that of the Moon or any smaller-sized space object. And because of our planet's constant rotation, there's an outward bulge on Earth. This tug-of-war between the gravity pulling inward and the planet's spin doesn't allow Earth to be a perfect ball. On top of Earth not being a perfect sphere, the planet is also tilted. This design flaw is responsible for the seasons we have. This tilt could happen because millions of years after Earth was formed, it probably collided with a protoplanet, a large space body developing into a planet. Venus is unique because it rotates backward compared to the rest of its peers. If you were standing on Venus, the hottest planet in our solar system, you'd see the sun rise in the west and set in the east. But you'd have to make it on time to observe this phenomenon. A day on Venus lasts for more than 240 Earth days. For a long time, scientists believed that the sun's strong pull on Venus was responsible for such a long day. But new theory claims that Venus used to spin just like Earth and the rest of the planets. But at one point, it just flipped its axis 180 degrees. It doesn't mean the planet abruptly stopped halfway through the rotation and started to move backward. One theory suggests that a large comet or object struck the planet in the past. This might have caused it to change the direction of its rotation, but many scientists doubt this theory. If you observe the moon for some time, you may notice that it's the same face staring at you every night. The truth is that the moon does rotate, but very slowly. It takes our planet's natural satellite 27 Earth days to rotate around its axis. Plus, the moon rotates at the same rate that it orbits Earth. The side we always see is called the near side of the moon, and the side that's not facing us is, you guessed it, the far side of the moon. It also has the nickname the dark side of the moon. Uranus's rotation axis is 98 degrees relative to the plane of the solar system, which basically means that the planet spins on its side. For a while, scientists believed that a large object firing through space knocked into Uranus, causing it to tilt. But here's one problem. Uranus's moons are covered in ice. A collision so powerful that it made the planet tilt would have resulted in disrupting the moon's movement and their position. But they seem relatively untouched, and all the ice covering them is still intact. But any major changes happening with Uranus would have generated enough energy to melt the ice. Another reason for Uranus's strange position might be its rings. Yup, Uranus has rings just like Saturn, except they're lighter and fainter. Saturn's rings are mostly billions of chunks of ice and rock floating in orbit. Some particles can be the size of a pebble, while others can reach the size of a house. Wow. Other particles are broken up comets, asteroids, and moons torn apart by Saturn's gravity. If you observe the rings from afar, they look like colorful stripes made up of thousands of different streaks, but there are actually only 8 layers of rings. Uranus might have had rings that were just as glorious as Saturn's around 4.5 billion years ago. The balance between Saturn's gravity and its rings might be responsible for keeping the planet upright so that it doesn't tilt over. If Uranus had the same rings, they could prevent the planet from toppling over. The way to solve Uranus's tilting problem might be for the planet to get its rings back. They would help Uranus keep its balance. On the other hand, hey, we like it just the way it is. So one day, Edwin Hubble discovered that the universe was expanding, so they named a telescope after him. Well, yeah, there's more to the story. Now imagine a fruitcake baking in the oven. As this cake is rising, the raisins inside are moving farther apart. Something similar happens when the universe expands, but instead of raisins, there are galaxies, which start to spread out. That's why if you randomly pick any 2 galaxies, the chances are they're moving away from each other. But then the question is, if galaxies are moving apart, why are there still galactic collisions? You see, even while expanding, the universe still remains a playground for galaxies to interact with one another, and they mostly do it by using gravity. All galaxies out there attract other galaxies, and their mutual pull slows down the speed of them moving apart. And naturally, the closer 2 galaxies are to each other, the stronger their mutual gravitational pull is. On a large scale, it doesn't seem to make any difference, since every galaxy experiences a similar pull in every direction. But locally, gravity kinda overwhelms this powerful cosmic expansion and pulls together 2 or more galaxies which were initially moving apart. That's how galaxy collisions occur. Plus, some galaxy groups, like the Virgo cluster, aren't expanding at the moment, since local gravity has stopped the expansion process in that region. Some large galaxies can attract smaller ones, and then the gravity of the larger galaxy starts pulling a smaller one toward it. Eventually, it leads to a collision. Galaxies are made up of stars, rock, dust, gas, and other materials. When 2 galaxies collide, their gases begin to interact. These gases usually exist in large clouds spread throughout galaxy systems. Because of their size, large clouds of gases are more likely to run into large clouds of gases. Then they start getting denser and experience more pressure. Or the combination of gases can cause waves, and the gases can collapse on themselves. Both of these processes lead to the formation of new stars. If 2 colliding galaxies are of the same size, many new stars are likely to form, making the galaxies shine even brighter. But if the speed of these 2 galaxies is too high, the newly formed stars can go right out after they appear in the sky. As 2 galaxies start coming closer to each other, they begin to stretch and deform, creating arms or tails. As a result, an elliptical galaxy can form, or the collision can form a new supergalaxy. In this case, stars from each galaxy will have to find a new place within this gigantic space formation. But of course, there are tons of galaxies that have never collided with others. That's because galaxies are actually relatively small targets in our gigantic universe. They form groups of small clusters where dozens, hundreds, or even thousands of galaxies gather together. Gravity holds them tight together, just like the solar system stays together thanks to the sun's gravity. Galaxies roam within these groups and clusters in a disorganized way. Naturally, collisions are bound to occur, but since galaxies are tiny compared to all that space they live in, massive mergers don't happen often. I'm talking about those collisions between equal-sized galaxies that shake things up on a grand scale. Of all the environments galaxies can live in, the most dangerous place is a group. Because solitary galaxies, living out in the field, seldom cross paths with others. As for galaxy clusters, they are indeed crowded. But galaxies in them move at such breakneck speeds that even if two of them meet, they'll simply race past each other without any dramatic consequences. But groups of galaxies are a different story. There, galaxies move comparatively unhurriedly. It makes it more likely that two galaxies in a group will not only come close to each other, but also get caught in their mutual gravitational pull for a prolonged time. And what will happen if two galaxies come close enough to collide? Well, the best way you can imagine such events is by thinking of them as merges rather than collisions. Galaxies are very spacious, and it's more likely that the stars they contain will just pass by each other. Let's talk about a galactic collision that, according to astronomers, is going to happen in several billion years or so. And our home Milky Way galaxy is going to take part in this space event. But don't worry, we still have some time to brace for the impact. Interestingly, there might be not one, but two collisions. And the first one might happen around, 2 billion years from now, when the Milky Way will collide with the Large Magellanic Cloud. This spiral of stars and dust is floating in space about 160,000 light-years away from our galaxy. And although right now this distance is totally safe and you have nothing to worry about, in approximately 2 billion years, the two celestial bodies are likely to collide. And what a view it's going to be! Imagine the Milky Way nearing the smaller galaxy. The supermassive black hole residing in the center of our galaxy will wake up and start gobbling up the stars and gas clouds of the Large Magellanic Cloud with enthusiasm. Thanks to this new food source, the hole will grow way bigger than it is now. It might even turn into a quasar, one of the brightest things you can find in the universe. Our newly awakened black hole will also be emitting long jets of super bright radiation. But people on Earth won't have anything to worry about. These jets won't reach our solar system. And even if powerful gravitational interactions triggered by the merger could probably fling us out into intergalactic space, the chances of this happening are slim. Like me winning the lottery. Stars are located too far away from one another, and even such a catastrophic galactic smash-up isn't likely to jostle our solar system. Now, if our black hole does turn into a quasar, it'll be an even more breathtaking view. The thing about these celestial bodies is that their light can be up to 10,000 times brighter than the light coming from the whole Milky Way galaxy. That's why Earth's night sky might change beyond recognition. The newly born quasar will get rid of some stars and send others flying billions of miles away from their orbits. As a result, all the constellations, as we know them, will disappear from the sky after the familiar stars get too far away for us to see them with the unaided eye. Luckily, the chances that the Sun will get knocked out of the Milky Way are really infinitesimal. But how about the predicted collision with the Andromeda Galaxy? Will our solar system survive this catastrophe as well? Right now, the Andromeda Galaxy is nearing the Milky Way at a speed of 68 miles per second. As you may guess, it's very hard to figure out its actual speed. And until 2012, researchers weren't even sure if the collision was going to happen or not. Unfortunately, it turned out that we had to prepare for the appearance of Milkdromeda, or Milkomeda, a structurally new galaxy consisting of the merged Andromeda and the Milky Way. Now, on the other hand, such collisions aren't something out of the ordinary if you consider galaxies' lifespans. Besides, even though the Milky Way is home to more than 100 billion stars, and the Andromeda galaxy contains about 1 trillion, the chances of several stars colliding during the galaxy's merge is really low. The reason is the same: stars are located too far away from one another. For instance, the closest to our Sun star, Proxima Centauri, is more than 4.2 light-years away, which is about 30 million diameters of our Sun. In simpler terms, if the Sun was the size of a ping-pong ball, Proxima Centauri would be the size of a pea located 680 miles away, and the entire Milky Way would be 19 million miles wide. Wow! As for other stars, can you imagine ping-pong balls hanging in space every 2 miles? Great! Now you have a miniature model of our galaxy.
You know how it all started 13.8 billion years ago with the Big Bang? Bam! No, wait, I can do better. No, never mind. And the universe has been expanding ever since. At its young age, it was all made of gas, mostly helium and hydrogen. For billions of years, the gas has expanded and cooled down. Meanwhile, galaxies, stars, and other mysterious things in space we try to explore today formed because of gravitational forces. And in that chaos, just like in middle school, about 4.6 billion years ago, our magnificent planet was born too. It all started as a disk of gas and dust that orbited the young sun, just the same way it was with the rest of the planets in our solar system. This disk consisted of dust particles of different sizes and gas. They were circling the sun at different speeds and in orbits that weren't stable and predictable. They were bumping into each other all the time. These particles grew from very small grains of dust into boulders, then later into bigger objects called planetesimals that had a range from miles to hundreds of miles in diameter. And these planetesimals that were orbiting the sun within the disk had gravitational force strong enough to pull other objects from the neighborhood out of their orbits and collide with them. As they were constantly hitting each other, they got bigger and bigger until some got to the size of thousands of miles in diameter. That's nearly the size of Mars and the Moon. We know these things because of meteorites. They come from different places all over our solar system and bring all kinds of materials to our planet, giving us something cool to study and learn about our solar system and how it formed. These materials include very small pieces of dust and rock that have gone through the chaos and survived those rough times even before the planets were created. Meteorites also brought pieces of asteroids and planetesimals left behind after the planet-forming process ended. As these objects were forming, some radioactive elements were left trapped inside the minerals that, again, were part of them. That's how scientists could tell how old they were. But the final stage of Earth's formation, and generally this whole chaos that was happening in our solar system, may have taken a little bit longer, possibly even up to 100 million years more. That's when the last enormous impact was, and the Earth finally reached its full size. What actually happened is that it hit another object which was nearly as large as Mars. This collision was so strong that the impact produced enough energy to vaporize some of the metal and rock, both from the Earth and the Mars-sized object. And this vapor created a disk that was surrounding our planet. That disk cooled and clumped together at some point, which is when we got our moon. Our moon was the result of impact debris, which was a combination of hot gas and molten rock. There are some theories of how the moon formed, though. One claims it broke off from the Earth. Another one says the moon formed somewhere else in our solar system, and at some point, as it was wandering around, it got so close to Earth that it ended up captured by its gravity. And fans of the third theory believe the Moon and the Earth formed at the same time, from the same protoplanetary disk. Before the Moon formed, the Earth was a much different place. If you could have just one day on Earth without the Moon, you'd be first surprised by the days and nights. They wouldn't be as stable as they are today because the Moon helps to keep the Earth's axis stable. Days were shorter back then. The Earth had been rotating much faster before the Moon formed. Its gravitational pull slowed the rotation of our planet, which means days got longer. The Earth's rotation is getting slower through time, but at a really small rate. Some predictions say that in 1 billion years, a typical day will be between 25.5 and 31.7 hours long. If 24 hours is not enough time for you, just wait 1 billion years. But yeah, if you're the type of person that likes to take things slowly, you definitely have to hurry back then. Although there weren't many things you could do back then than to fill your time, besides, sailing across the hot lava, collecting rocks, or hoping not to get hit in the head by some fierce meteorite falling onto our planet. Ow! But if you were patient enough, maybe you'd see something really cool: water coming onto our planet for the first time. There was a rain of fiery meteors coming from the sky, and they kept slamming into our young Earth. It looked devastating at first, but some of this falling debris probably held water. Many believe the asteroids and comets that bumped into our home planet carried tiny amounts of water. But considering this meteorite shower lasted more than 20 million years, maybe even up to 200 million years, it's not that unusual that after a while, puddles of water started to collect across the surface. And as the water evaporated within the atmosphere, it would fall back down, forming lakes, rivers, seas, and eventually oceans. Only at that point, there was a chance for some primitive life to evolve sometime in the future. Earth started its transition from a hot ball of magma to the world we know today. Before that, it would be too hard for life to exist there. Even if it had happened somehow, all those meteor and asteroid collisions would have probably destroyed it. Also, you wouldn't be able to survive without an oxygen tank. The Earth did have an atmosphere, but it wasn't like the one we have today. Scientists believe it was composed of water vapor, methane, ammonia, and some other gases released from volcanic activity. Basically, it was too toxic, since there were volcanic eruptions all the time. And the temperatures were way higher, so just standing at these early stages of Earth wouldn't be such a pleasant experience. Also, there could even be some form of life at that time. In its early stages, when everything was so chaotic, it wasn't covered in oceans, trees, or stunning landscapes like today, but in molten magma. I mean, the earliest form of life we know about are fossils of microorganisms found in hydrothermal vents, and they're thought to be 1.4 billion years old. And scientists assume the earliest time for life to show on Earth could be 4.2 billion years ago, give or take. So, with the right equipment, you could even see some single-celled organisms like bacteria somewhere across our chaotic planet, even before the Moon was there. The Moon's gravitational pull on the Earth creates tides in the ocean, which means it probably helped mix and circulate ocean water, maybe even shape them. The tides without the Moon would be much smaller, because the gravitational pull is what causes the tides to rise and fall. The Moon also affects life in the ocean. Over time, animals in the ocean have changed and adapted to the changing water levels caused by the Moon's gravity. Even just the moonlight has a big effect on sea creatures. For example, corals use the Moon's cycle to release their eggs at the same time and with stronger tides to help carry the eggs. Baby sea turtles use the Moon's light shining on the water to guide them from their nests to the ocean. Who knows which directions life on the Earth would have taken if, at some point, billions of years ago, we didn't get our lunar buddy to follow us along the way.